decided to give out an award starting from this year regularly at EvoStar for someone who should be rewarded for their work in the field, and preferably in connection with how Julian thought about evolution. So let me just remind you of this award rules. So the Julian Francis Miller Award will be given to someone for important contributions to the algorithmic exploration and embodiment of evolution, development, and or learning. It is an award given with a plaque and a cash prize, and anybody in the scientific community may nominate someone for this award. Now, we give it once a year at the EvoStar conference. And here are the timelines that we have worked on for this first selection. July 1st, and that will 31st, that will stay for the future years as well, will be the nomination deadline, and was the nomination deadline last year. And then we have a committee that makes a recommendation to the Society's executive board, which decides by November 15, and then the award is supposed to be delivered at the regular EvoStar conferences. There's more information on the rules on this website. And as I said, this is an award that's given every year. So please think of colleagues that you want to nominate in the future and merit this possibly, and send them to the appropriate nomination form. I think the nomination form right now is still from 22, so we'll have to update that. Our award winner this year was already announced. It's Professor Susan Stepney, and here is the citation. Susan Stepney has developed theory, framework, and algorithms for the evolution and the development of evolutionary algorithms, helping to form the basis for current research into emergence. And Susan, you're very welcome to give a talk here. Do I have another slide? Yes, I have another slide about Susan. Namely, she's a professor of computer science at the University of York, which happens to be the place where Julian worked for about 10 years or 15 years. I forgot exactly how long. She's an astrophysicist by training, now computer science professor by profession, and an interdisciplinary researcher by heart. She's the director of the York Cross-Disciplinary Center for System Analysis, which, as far as I remember, had a different title before, but the acronym has changed. And she's a good colleague and was a good friend of Julian. Susan is a deep thinker on computers, matter, life, evolution, emergence, novelty, artificial life, and many other topics. Very interesting person. Avid reader, fan of books, and notably of science fiction. Susan, please come to the stage. Thank you.
Well, as president of Species, it is my pleasure to give you the award. This is a small certificate, okay? And I think we need to hold it. More importantly, a voucher for 3,000 euros that comes with the award.
That'll send some students to some conferences.
Yes, that's the right way to spend it. Congratulations.
Thank you very much.
It's really a pleasure.
Yes. Thank you. Did you turn on your mic? Yes. So I just need some magic to get the right slides up. Please wait. Okay, thank you very much. I'm very honoured to receive this award. Julian was a good friend and colleague, and we miss him deeply. And he was an outstanding scientist. And as many of you know, he was the inventor of CGP, the Cartesian genetic programming, a representation of networks that allowed many fruitful explorations of evolution. Fewer of you might know that he was also a pioneer of in materio computing, using weird materials to perform computational tasks. We actually co-supervised 2 PhD students together, one on subsymbolic artificial chemistry and one on using carbon nanotubes for in materio reservoir computing. And today I'd like to honor his memory by talking about some of these ideas that have grown out of that reservoir computing work we did together. And I like to think he would be interested in these ideas. So, beyond reservoir computing, metamaterials and metadynamics. And I hope by the end you'll understand how those words go together. So first of all, because I'm talking about reservoir computing, not everybody will know about it. I'll give a little bit of background of what in materio reservoir computing is, and then I'll move on to how we can potentially move beyond that. So just the reservoir computing model itself, well, the echo state network reservoir computing model I'm going to talk about, the underlying computational model, the concept, is it's a random recurrent neural network. And with the emphasis on the random. And what's interesting about this here, I'll just get, for those of you who prefer maths to pictures, I'll just, it's the standard recurrent neural network equation. You have the internal state X at time t, you multiply it by the internal weight matrix, which remember is random, and then you add the input through an input weight matrix. And apply a function, which is usually a tanh function, something like that, to give you the state at the next time step. So it's a discrete time random recurrent neural network. And then the output at the next time step is the observed internal state observed through the output weight matrix. And so one thing I want you to take away from this is that it's one instance of an open dynamical system. It's a discrete time, open dynamical system. It describes the time evolution. It describes, it has an input, and it's discrete time. This will become important later, maybe. So the important thing about this, it's a recurrent neural network. And so how do you train recurrent neural networks? They're notoriously difficult. But here, it's got a different training algorithm from what you might expect. The internal weights and the input weights are chosen at random. And the only thing that's trained is the output weights. And the output weights are trained by simple one-shot linear regression. So you put your training data in, you only have to present the training data once. You do a large calculation, a large matrix, which you do a pseudo inverser on, plus some technical details I won't go into. In order to train it. So it's really good for quick training of this recurrent neural network. But another interesting point that I want to highlight here is that you can use the same reservoir, the random reservoir, and only use different output weights for different tasks. So you've got a reservoir sitting there, and it's only the output weights that are kind of the program of saying what that reservoir is actually recognizing. And this might sound a bit weird. What's going on inside is it's a dynamical system. It's projecting the input into a very high dimensional space, such a high dimensional space with lots of stuff going on that you can just train a simple linear recognizer on the output in order to do the classifications or whatever it is that you want. And what's important for in materio reservoir computing is that this recurrent neural network inside does not have to be emulated on a digital computer. You can actually use a physical dynamical system as the reservoir. This is the weird materials. As long as it's got sufficiently rich properties, you can use a dynamical, any material that reservoirs. And so there's a lot of work going on about trying to find different materials that reservoir well. Because it's a black box and you only need to train the external weights, that's why this approach works. You merely need a material with rich enough nonlinear dynamics that's excitable by an input stimulus and has a readable output state. And it does also help if the single instance can be configured into different reservoirs, but I won't go into details about that. And so here's a zoo of different hardware that people are using. People use, we've used carbon nanotubes. We're currently using magnetic materials. Other people use memristas. Other people use slime molds. There's basically nearly everything can be made into a reservoir if you actually want to. So that's reservoir computing. So dynamical systems computing. Well, why am I talking about dynamical systems computing in general here? Well, classical computers, it's like having a field full of sinkholes, okay? And each sinkhole is a state in the computation. And what you do on a clock tick is you jump to the next sinkhole. And then on the next clock tick, you jump to another sinkhole. And this is really inefficient. I mean, that was really hard actually for me to do that because you haven't got any momentum, you stop. It's quite useful to being able to stop because you can then debug and look at what's going on. But you've not got any momentum. You just stop and wait for the next time you're kicked into the next sinkhole. This is one of the reasons why classical computing is quite power hungry. But a different model, maybe using a dynamical system, imagine instead of a bunch of sinkholes, imagine the computational state being a ball rolling down a hill. And so gravity is pulling it down the hill. It's going down a rugged landscape, and that landscape is kind of the definition of the computation that the ball is doing. It's reminiscent, those of you who might know about Waddington's epigenetic landscape of how cell differentiation might happen. The ball can roll down one valley to become one kind of cell, or it can roll down a different valley to become a different kind of cell. So that's the kind of the idea of using a dynamical system. But you actually, for computing, you want an open dynamical system. You want to be able to put some inputs into it as well. And that might be thought of as some kind of force on this dynamical system, like a wind blowing a ship around, or a wind blowing, so the ball falls by gravity down, but the wind can maybe blow it a little bit back uphill. It can maybe blow it harder so that it goes over into a different valley. So the input is kind of providing some kind of kick. And in Waddington's model, actually the landscape has got a bunch of hidden guy ropes underneath, which is kind of the next level metadynamics of being able to change the landscape itself and changing what valleys actually exist. And so in a sense, what you need for one of these open dynamical systems is a material that wobbles in an interesting way when you kick it. So the input is you kicking it, and then the material wobbles. That's the kind of response to the kick, and then you can observe it to see what computation that it's done. And so, as I said, reservoir computing is one of these kind of systems. It has an open dynamical systems model. It is a discrete one, but there are continuous ones. And the idea is that you use a computer to directly exploit the dynamics of the physical system. And that means you can integrate the computation being done with any other dynamics in this system that you might want to exploit. For example, in a sensor, and I'll give an example later, or in a robot, so the dynamics of the body and the dynamics of the computation can be integrated into one kind of thing. So that's the computing really becomes an embodied part of the overall system. It's not just a bolt-on, it's not a brain in a box bolted on, it is actually part of the body. So it's kind of a way of rethinking computing. Why would you want to rethink computing? There's this famous quote in computer science. Computer science is no more about computers than astronomy is about telescopes. It's not quite clear who may or may not have said this. It's often attributed to Dijkstra or sometimes to Perlis, but actually when you try and track it down, it sort of fades away into something. But this is a well-known quote, and especially true of those computer scientists who have a more mathematical bent than others. And I assume that what they mean by this is that computer science is not about computers any more than astronomy is about telescopes. I assume that that's what they mean. As Wolfgang said, I was trained as an astrophysicist. I've never actually observed. I was a theoretician, but still there were a lot of telescopes around. So all of these well, apart from one of them, all of these telescopes are relatively recently. This is an optical telescope, a huge optical telescope. It's a 40-meter mirror. And when I was doing astronomy, it was proved that it was impossible to build a mirror this big, but there are computers underlying it, so that's fine. And this has the very imaginative name of the Extremely Large Telescope. That's an optical telescope, and we're used to looking out at the sky and seeing things, and all this does is allow us to see further. These are radio telescopes from Jodrell Bank, the single one, to this bigger array of telescopes, imaginatively named the Very Large Array. Astronomers are not very good at naming things. Opened up a whole new window on the universe. Then this is a gamma ray telescope, another new part of the electromagnetic spectrum has to be put up into space because the atmosphere is notoriously opaque to gamma rays. And then more recently, this is LIGO, the gravitational wave observatory. So this is just a whole new modality of telescopes. So there's lots of telescopes there. So why am I telling you about telescopes? Well, they're windows onto our understanding of the world. And there's this famous quote from William James, which I really like, talking about how different beings will perceive the world differently. And it's this other sculptors, other statues from the same stone, other minds, other worlds from the same monotonous and inexpressive chaos. I'm not quite sure whether the world is monotonous and inexpressive chaos, but that he was talking about that. But the idea that my world is but one in a million, embedded alike, real to those who are experiencing them. And then he says how different must be the worlds of the consciousness of the ant, the cuttlefish, and the crab. Okay, so here's some ants, cuttlefish, and crabs. If we think back to what I was saying about reservoir computers, that it's only the output weights that you train, let's, instead of making the output matrix part of the reservoir computer, let's make it part of the observer. So now we have a big reservoir computer in the middle, a big complex dynamical system. Then we have different creatures who've got different output weights, almost like different pairs of spectacles to look at the world. So there's mine, and I can see I can see a particular scale, I can see a particular part of the electromagnetic spectrum, I've got other senses and so on. But an ant is going to have a very different output weight matrix. It's going to be able to see things on a different scale. It's got its pheromones, so it's using scent a lot more. Cuttlefish, I have no idea what they do, but they certainly change color, and they seem to communicate by the color patterns on their skin, which is a very different way of observing the world. And then crabs, they presumably see everything sideways or something. I don't know. But the idea here is that we've got windows on complex dynamical systems, very different windows on these different dynamical systems. And so these physical systems, as opposed to mathematical systems, these physical systems are giving us different windows on computation. So we might extend James' quote to other computers, other models of computation. So here's an example of how we can see things differently. This is a fairly classical view of what embedded computing looks like. You've got your sense, compute, actuate pathway. And your sensor typically is some kind of analog device because it's interfacing with the real world, which tends to be analog on many scales. So here maybe a microphone or a camera. And then, of course, in order to get it into your digital computer, you've got to do an A to D conversion to take your analog signal and put it into a digital signal that the digital computer can process. It computes away, it does whatever it does, and then it needs to do something. It needs to output this maybe to an actuator, which again is analog. So you've got to do a digital to analog conversion. So not only do you have your digital computer that's a little bit energy inefficient because it's full of sinkholes that it's jumping its state between, but you've got all this inefficient conversion going on as well. But we can rethink this if we think about dynamical systems, in particular, in this particular example, reservoir computing again. So MEMS, electromechanical systems. You can have microscopic oscillating coupled beams. The way your airbag in your car works is using one of these devices, it senses an acceleration. So when you slam into something, there's a very sharp acceleration there. It senses that and deploys the beam. And the way it senses it is this little beam starts wobbling really fast. And so accelerometers, but gyroscopes use these devices as well, microphones and so on. And you can use one of these beams as a reservoir computer. Ignore the thing about delay line, I didn't cover those, but that's a way, it's a particular kind of reservoir computer. So you can actually, instead of using it as an accelerometer, you can excite it with some input signal, say an electrical signal, and use it as a reservoir computer to do various calculations, because it's a nonlinear dynamical system, which is basically all you need for a reservoir computer. But then what you can do is think, well, I'm using it as an accelerometer. It responds to input, acceleration input. I can use it as a reservoir computer. Why not do both? Why not use the input driving of your reservoir computer being that very acceleration? So you're driving the computer directly with the input. So your sensor is now not just sensing acceleration, it's computing something about that sensed acceleration in the very same device using a dynamical systems approach. So the acceleration excites the beams, which are then used to compute something about that acceleration. And so this is how you can have some kind of integrated dynamical systems approach to thinking about computing, but now we're computing in an embodied sense. You've got a system that's excited or driven by the input. This also gives you some power efficiency because some of the energy to do the computation is actually coming from the driving force. So for example, the sound waves might be exciting the material somehow. And then you can process that excitation directly using something like a reservoir computer or another dynamical system. Interestingly, the output can be in a different modality. You could potentially have sound coming in and electricity going out. So you can also integrate transduction in the very same device as well, and then directly connect that to an actuator. So there's no A to D conversion needed anywhere. So one application that people are thinking about these reservoir computers is as low power edge computing devices. You can have smart sensors or smart actuators that can do a little bit of processing. And then if they say to themselves, well, actually, I've done a bit of processing and there's something I need a bit more help, then you can farm it out to the digital computer. But the majority of the stuff can be done at the edge. And so that's one of the ways. So if we go back to computer science is not about computers anymore than astronomy is about telescopes, I completely agree with this, as in computer science is as much about computers as astronomy is about telescopes, because thinking about different ways of building computers gives us different windows onto computation. Telescopes give us different windows onto the universe at large. These different ways of thinking about computing give us different windows onto what actually computation might be. So with rethinking computing, moving away from the digital paradigm to the dynamical systems paradigm, So there's two steps in this rethinking that I want to talk about, which are more relevant to people here. There are lots of other steps as well, but two steps I'm going to talk about. If we think about these kinds of devices, we've got open dynamical systems. So they need to be open because they need an input, but they're embodied in, as I said, weird materials. Okay, so metamaterials. So what's a metamaterial? So a metamaterial, we want material that's got both structure and dynamics. So it's got some potentially complicated structure that can encode information, but it's got the dynamics as well that it can use to exploit and process that encoded information. So you need the matter to embody the dynamics, and the material structure enables the dynamics. So biology is a great example of this. It's got highly evolved biopolymers all over the place. So I have got the word evolved in here, but it encodes information in DNA and RNA, which enables functional dynamics through the RNA and the proteins. So DNA, RNA, and proteins are highly evolved metamaterials. But normally the word metamaterials is applied to engineered structures, stuff that we build, not necessarily stuff that evolution has evolved. And normally, metamaterials talk about functional properties, strange electrical or optical or mechanical properties, but we can also think of them as also having novel computational properties as well. So the functionality that they've got is a computational or a processing functionality. So in materio reservoir computing is exactly one of these things. You can have highly engineered materials that have the kind of dynamics that you want that makes a good reservoir. So smart functional materials that have both computational and functional properties. So again, we're not just saying, I want to engineer this to be a specific reservoir with these computational properties. I'm saying, I can engineer this system to have both the computational properties and then the functional properties that are needed to do other interesting things as well. And so there's a complex intertwining of the computation and the functionality. And I think part of the issue with a lot of computation is we came up through the wrong route. We came up through the sort of the Turing, very black box route of doing little calculations, doing our tax returns, doing our spell checking and so on, which is all very disembodied. But the majority of computation that's happening in the natural world is very much an embodied approach. And we need to think about the embodiment of the computation in other stuff that is doing other things as well. So, so what we've got then is we want to think about computation happening as an embodied process in these highly engineered or highly evolved smart functional metamaterials. So step 2, constructive open dynamical systems computing with metadynamics. So this is then taking what I've been talking to the next level. So the stuff I've talked about up until now has been fairly standard stuff. And now I'm going to get a little bit more speculative. Okay, so a constructive open dynamical system means that we also include processes of change and growth. Now, in classical nonlinear dynamical systems theory, there's stuff that you get if you take a book off the shelf on that. You've got a fixed state space, and it's analyzed in terms of attractors, bifurcations, chaotic behavior. You might have strange attractors and so on. Then the open, you add openness to that. So you have the driving inputs and you have outputs and you can have feedback loops and interesting things going on. But the constructive part also, or sometimes called developmental dynamical systems, the state space itself changes as a result of the dynamics, either as a direct result of the dynamics or as an environmental or other input that's changing things. So you end up with dynamical systems that themselves have dynamical structure, which is the metadynamics, the dynamics of the dynamics. So you're thinking of your state space as being normally you have a state space which has got a state component in it and a trajectory through that state space. Now you want to think of a meta state space where the points in that meta state space are state spaces, and you have a trajectory through a set of state spaces. So that's the metadynamics, and they can have very separated timescales, and that's fine. That makes life a lot easier because then you can assume that the state space is fairly constant until a point where it needs to change into a different one. But if they have similar timescales, everything's shifting under your feet as you go. So yeah, I said, so the state space changes as a result of the dynamics. And there are different ways of doing this. There's you can have a state space with some parameters in it, and you can change the values of those parameters, which might change some scaling. It might actually change something like a decay timescale or a feedback timescale, or it can change how chaotic the system is. So the picture on the right there is the Reservoir attractor for different values of the parameters, and you can see in some places it's the trajectory is just a limit cycle. Then a bifurcation steps in and you've got a doubled cycle. And then for certain values of the parameter, you end up with a strange attractor. So you're actually changing a parameter. You're not changing any input to the system. You're just changing a parameter of the system. The guy ropes under Waddington's epigenetic landscape can be thought of as metadynamics. As you change the tension on the guy ropes, you're actually changing the shape of the space. So you're changing the dynamics that can happen in that space. And then, and so those are relatively straightforward. You've got a state space that's parameterized, but is at least of a fixed dimension. And then things get really interesting when you start adding growth to the system, because now you are changing the dimensionality of your state space as you go. Now, for mathematicians, this is screamingly frightening because you've maybe defined your state space maybe with a set of differential equations, one for each component of the state. Now you've got a new dimension, you need a new equation. How do you write a mathematical system that adds a new equation into the system as you go? Computing, we're quite happy to do that. We're changing the dimensionality of our state space all the time. You just go new or alloc or something, and suddenly you've changed the dimensionality of the space. But we're not very good at actually analyzing what then goes on, because we're still jumping between the sinkholes in that different state space size. So, so the metadynamics is the dynamics of the state space changes, and then you have meta trajectories, where the metastate variables, as I said, are themselves state space. So this is a very conceptual view of what's going on. You start off with a point attractor, you change a parameter maybe, and then you get a limit cycle attractor instead, but maybe you change another parameter that suddenly moves you into a different dimensionality, and then maybe you change another parameter that changes how chaotic that is, and then something else happens, and away you go, and everything is getting quite weird. So the reason personally I'm interested in this is the stuff that Wolfgang talked about, embodiment and emergence, is thinking about computation as a whole in terms of machines that move from being mere machines maybe up to living machines. So what I call a mere machine, because very often we talk about you know, because say, well, I'm a meat machine. I'm just a machine. I go along. People say I'm not a mere machine. No, we're not mere machines, and I'll say what a mere machine is. But we are machines. So a mere machine is something like a you know, cogs and wheels in a factory. You've got dynamics, but the dynamics tend to be cyclic. They perform the function. They go around a cycle and produce a widget. They go around a cycle and produce a widget. They go around a cycle and produce a widget. And the metadynamics they have is essentially trivial, and it's extrinsic. They might have they might slowly wear out and have to be repaired, but they can be reset. You can switch them off and switch them on again, back into their original state. Then maybe the next level up are computers, or today's computers. They have a non-trivial dynamics. I'm now thinking here of classical computers where we know they have a non-trivial dynamics because of undecidability, halting problem, and so on. We know that we can't prove in every case what they're actually going to do. and they're open, we can put inputs in and get outputs out. If we can't put inputs in and get outputs out, they're not really computers. They're not doing anything for us. But they have a simple metadynamics. You can program them so that their state is different, so that they look a little bit different, but you can switch them off and on again. And you can actually do a factory reset and switch them back to what they were when you first got them. So although in some sense they've got a metadynamics that is changing what's going on, you can set them back. But then a living machine, it also has a non-trivial, unpredictable, and open dynamics, but it also has a non-trivial metadynamics. And that's the point that I think is where the difference comes in. It's the metadynamics itself is unpredictable and open and irreversible. You can't switch us off and switch us on again. Modulo may be giving a, when somebody's heart is fibrillating, and that's actually what they do, is they switch you off and switch you on again. But that happens very quickly. But it's irreversible as well. We age, and we can't unage, and that's what happens there. So I think if we analyze machines in terms of their dynamics and their metadynamics, we can see a route from going from mere machines through computational machines to machines that are more living, where the computation is truly an embedded part, an embodied part of the overall machine. So this is the way I'm interested in rethinking computer science. So tomorrow's unconventional computer science will be about open computational dynamical systems embodied in smart functional metamaterials that have non-trivial metadynamics. And in order to do this, we're going to have input from a whole raft of different disciplines, some of them listed along the bottom there. And I just want to say, I know Julian was interested in lots of things like this, and I really do think he would be interested in this kind of way of moving computer science forward. So thank you.
Thank you, Susan. I think we have time for a few questions. Please, Gabriela. You get the mic.
Thank you, Susan, for such a nice talk. Two questions. One, I was curious, you mentioned your background in astrophysics, seems such an interesting topic. I'm just curious why you decided to change to computing. That's the first question. Shall I ask the second?
Well, shall I answer the first one?
Okay.
And then, because otherwise I'll forget it, because this I'm talking about, 40 odd years ago. There weren't a lot of jobs in astrophysics, and I thought maybe I really needed a job, a proper job, and so therefore I had done some Fortran 4 programming during my PhD. Sorry, I just got away from Bill there. Fortran 4, good old stuff. So I used that to blag my way into a job in the computer industry, and I stayed in the computer industry for about 20 years. And had a great time, but doing lots of different things like formal methods and so on. And then I got the opportunity to move back into academia. And so I thought, I'm in academia. I don't want to do all this straightforward stuff. I'm going to do something bonkers. So which is why I'm doing this kind of stuff now.
Okay, so the second question is, we are in a bio-inspired topic. And I was wondering whether this type of new computation, if there is some form of living things that are, I know, for example, octopuses, they don't have a brain, they have the nervous system seems to be distributed. So I wonder if there is some biological creatures which have this type of computation.
It's fascinating you mentioned octopus, because that is one of the soft robotics inspirations, and some colleagues in Japan have been doing some fascinating work with synthetic octopus tentacles, I'm pretty sure, and they put them in water and they excite them at the top and they wiggle around. It's very difficult to do an octopus tentacle because it's all sort of all smooth, but and they wiggle it around and they can use it as a reservoir computer. And that's part of the basis of the inspiration. Well, if the body can be used as a reservoir computer to do something that we want to program it with extrinsically, can it also be used as a reservoir computer to control itself through its own feedback? And they're beginning to do some work on that and say, yes, that there does seem to be a lot, these kind of spectacles that we use to look at the world give us a way of also looking at the octopus body to say, yes, it can be used as a computer. Is it doing its own computation? And that's where we're wanting to go, is to find a way of using the dynamics of the system as part of the control, but then using the metadynamics as well, maybe through environmental inputs. And an easy example of that is something like gait change. So moving from a walk to a trot to a gallop is a sort of metadynamical change, because you're changing the dynamics quite considerably, but it's a kind of fairly discrete one. I mean, we know how to do that with things like central pattern generators and so on, but it's those kinds of things. Can we get environmental feedback as you grow, as you get damaged? How can you actually use those kind of ideas to continue to control the body?
Thanks so much for the talk. So I wanted to ask a question that is going to talk a little bit about the C word that maybe is not allowed to be said here, consciousness. It's often said that computers will never be able to be conscious and fully intelligent, intelligent. But it's a matter of not having the right substrate. Like digital computers, silicon-based computers will not be able to be conscious, which I sort of agree with. But it's just a matter of we don't have the right substrate. We haven't found it yet. And the follow-up, it's are there any other substrates out there that we haven't found that would be more effective than silicon or neurons?
Well, it's this highly engineered substrate. So neurons are highly engineered through evolution. Silicon, I mean, the silicon chip is probably the most highly engineered computational metamaterial we've got. I mean, it's pretty good. I think that, well, one, I have a problem with consciousness because I've never heard the definition of it that I understand. Two, those are higher functions, I think, and I'm really interested in the lower level stuff. So I come from sort of the artificial life background, which has the strapline artificial intelligence from the bottom up, and I'm much more interested in the bottom layers than some people go. Oh, I can do an ant right now. I can go straight up to the brain. But you can do an awful lot of computation in the body, but you probably do have to farm some of it out to a higher level. And I think as soon as you've got a sufficiently complex system here that it can make a model of the world that it needs to do in order to anticipate problems, puts itself in that model and starts thinking about itself, there may be, depending on what your definition of consciousness is, that's kind of when you're there. And I'm not convinced that there's any difference between silicon and carbon at that point. It's just the complexity and the recursiveness of the model. But hey, I don't know.
Thank you very much, Susan, for the wonderful talk. My question is about the definition or the concept of living machine. Would you say that large language models, not alone, but together with the human society, are a living machine, in particular concerning the second part of the definition, the metadynamics part?
I don't really know enough about large language models, but the point that you made about in combination with human society, this was something I was actually going to add there. I think part of the issue is needing to be embodied in a complex environment as well. And therefore a brain in a box is just going to be, is not going to have those kinds of abilities to understand the world, to be able to ground its symbols in their semantics in the world and so on. So, so I think a large language model in a box is just something that's doing its thing. A large language model in a society that's feeding it different inputs, where the environment's changing all the time and so on, might be part of a larger machine, but I don't really know enough about them to be able to say more than that.
Hi, Susan. Hi, Daan van den Berg from VU and UvA Universities in Amsterdam. I have a very cliche question for you, latching on to basically everything that other people said. Do you think that the brain, the human brain, I mean, in artificial intelligence, sometimes we're pretending to like actually build the brain instead of mimicking the behavior, right? Do you think that the brain is like a jumping, discrete computation machinery or something else?
I don't know. Clearly, it's got different levels of virtual machine in it. So I don't know if any of you know the work of Aaron Sloman talking about his different layers of virtual machines and starting off with something relatively continuous and getting more and more sort of discrete and so on. Most of the brain isn't there to do the kind of computation that we think of as computation anyway. I can't remember who it was that said in one of the talks, 80% of our brain is for moving our bodies around and 20% is maybe for playing chess and Go, which is much easier to do on the computer. I think when we start thinking about true embodiment of computation in other functional matter, we have to take into account that there's other stuff going on as well. And an awful lot of the brain is there to keep us alive and not just. We're academics, we think our brain is there for us to think deep thoughts, but actually that's not really what it's for. That's just an epiphenomenon on the top, because we've got, we've got some extra power that we're not using to fight the tigers.
So actually, what I was thinking myself when you were talking about this is that the brain, the neurons themselves, they communicate with spike trains, right? And these spikes, they are rather discrete. It's like either a spike or non-spike, but maybe the time in between is continuous. So therefore, I was just pondering about like, are the computers we use, are they actually suitable for mimicking true brain behavior or no?
So that's really interesting, because of course there are spiking neural networks and so on. And also there's a reservoir computing model. I said, I'm talking about the echo state network, which is a discrete time one. There's a different model called the liquid state machine, which is a spiking model, reservoir computing model. And it's called reservoir computing because one person invented one form and one person invented the other, and they decided they were related. So they gave it a name. No idea why they called it reservoir computing, but yes, should it be discrete or continuous? Where is the continuity? The problem with continuity is that you often end up with unary encodings, which are very inefficient. The lovely thing about digital machines is you can have a really good binary encoding, which gives you that logarithmic advantage in space. So I think hybridity, rather than saying this is the right approach, we'll do everything that way, is to say, no, this bit works well for that, that works well for that. This embodied part works with a bit of feedback from your reflexes. This part is a higher cognitive function. This part needs to be farmed out to a supercomputer somewhere else. We ought to be thinking about hybrid systems where we have lots of components, each good for what they're good for. Liquid state machines, yep.
Thank you very much, Susan. I have a last question for you, maybe, if I'm allowed, about the metadynamics. You mentioned that metadynamics can, non-trivial metadynamics can be, at least part of it can be implemented in computers where you have the ability to produce new states, or new memory and so on. And you say that the mathematics of it, I mean, the mathematicians have a headache about this. And could you comment?
Yeah, so they're two quite different models, because the model in computing is your discrete system, and therefore you can get a new dimension on the next time step. Suddenly a new dimensions appear. The mathematical way of doing most dynamical systems tends to be continuous systems modeled through differential equations. So it's a continuous time model. Interesting. How do you get a new dimension? Things grow. If you want a new dimension, how do you get that new equation explaining what it's doing into the system and so on? So it's not, it doesn't fit naturally into that way of doing the modeling, but there must be a way of doing it, because after all, when you actually think about something like cell division, discreetly, you can say, I've got one cell, in the next time step, I've got two cells, but obviously in between, there's some mess that's happening. And in fact, cells are even worse than that because they're starting to divide for the next time before they've even finished dividing the first time. So they don't fit models at all. And that's the thing to remember. A lot of this stuff is just our model of what's going on. And sometimes we get a little bit too invested in the model itself rather than in what we're trying to model. And so we work out properties of the model that are not properties of the real system because we've made approximations and so on.
Thank you very much, Susan, for a wonderful talk. I think, thank you very much. Yeah. I think we have a student session now.